Hi everyone, and welcome to today's session. Today, I'm very pleased to have Micahel Hodel here, who is currently in the leading team of the ARC Prize, and he has engineered an awesome method to re-engineer ARC challenge puzzles. So I knew Micahel because I've been doing ARC, and he reached out to me, and he's more or less like a spokesperson for the ARC community. He collates different solutions, attends various conferences, and I'm very pleased to invite him here to share more about what he has learned and what he has been doing. So without further ado, I'll invite Micahel to start sharing.
Well, thanks a lot for having me. Let me know if you can see my slides.
Yeah, it's good.
Sounds good. Well, I'm gonna spend a little bit of time first to talk about the DSL, as it's kind of slightly related to my re-arc work, but also some people may be interested in that. But yeah, just about 5 or 10 minutes or so. I'm just gonna assume familiarity with the ARC benchmark and basic terminology here. So yeah, here you can see one of the kind of more well-known puzzles and the corresponding solution program that I wrote using the DSL that I created. So I really kind of just set out to do what François outlined as one of the obvious first steps one should be thinking of doing, which would be creating such a language that you can use to construct or compose programs that can solve ARC tasks. So yeah, the goal is really like create a set of functions that's useful for creating such programs. And obviously the main idea why you would want to do that in the first place is program synthesis. And at first I just wrote down a set of functions that I thought would be useful without like having any specific ARC task in mind. I mean, if you've ever gone through those tasks, you'll know you probably want to implement some rotation function or whatnot. And yeah, then it was kind of an iterative process where I just refined the DSL and added more solution programs over time. So the DSL kind of grew organically. And yeah, basically the outcome of that is 160 primitives and corresponding solution programs for the training tasks.
Micahel, sorry, just to ask a bit. So for those who are not too familiar with the ARC, maybe you could give a brief background about what ARC is, and also like what exactly constitutes a DSL, a domain-specific language.
Yeah. I mean, ARC is just this, it should be a benchmark for intelligence, but it actually just stands for Abstraction and Reasoning Corpus. It's like a set of 1,000 reasoning puzzles where you're given like a handful of demonstration input-output pairs, and then a test input pair, and you have to infer kind of the rule, the transformation rule from input to output, and apply that successfully on the test input. And yeah, it's somehow non-trivial to do with machines. So that's also why it's interesting, or at least partly to me. And the DSL is really I mean, DSL stands for domain-specific language. The goal is that, let's say you want to do program synthesis, sure, you could think of using any programming language as your base, like Python. But the kind of space of possible programs is way too big, or it's kind of not really adequate to do program synthesis for this kind of domain. Yeah.
I got it. So in other words, your bet is that all these arbitrary puzzles that François has collated for ARC, your bet is that a small set of primitives would be able to solve every single problem if applied correctly, like shift the square to the left, change color, those kind of primitives would be able to solve every single ARC problem. Is that right?
Yeah, that also has held up so far. I mean, and all you kind of need is a Turing complete language. For sure, you're gonna end up with some tasks where it's like kind of harder to find a neat short program. But it's not all that hard to come up with some set of functions which is kind of expressive enough to construct any solution. Yeah. Either way, like I just try to keep this language such as like yeah, powerful in expressivity, right? but also there's like abstract and generic. I don't want to have 500 primitives. And also if I have a primitive, it should be not just useful for like 1 or 2 tasks, but more than that. I'm not going to go into too much detail here, but people feel free to ask questions about that. But the focus should not be the DSL. I just want to give some background on that. Yeah, kind of, if you try to classify these 160 primitives, about a third or so are transformation functions, like the obvious ones. You can transform some object or some grid, right? Another about a third, I'd say, are properties. So give me the height of a grid or the number of pixels in an object or whatever. And then there's a whole lot of utilities. So the DSL is not very homogeneous, so to speak. There's set operation stuff like arithmetics, like all the basics. And a whole lot of helper functions, like maybe you want to do branching or you want to filter a container, and so on. Yeah, proof of concept is like solution programs for the training tasks. Then I just kind of try to minimize the length of those solver programs. That's also kind of how the DSL creation was guided. And why did I do that? I mean, sure, on the one hand, you want to have a small DSL, but you also want the programs you can create with this DSL to be small. Otherwise, it's kind of infeasible to do program synthesis or any kind of search. Yeah. And I guess this could be a useful starting point. Like if you, as I said, want to do program synthesis or also program mutation. Yeah. Ideally, they would all look like this. This is task, input, output, and corresponding DSL program. So quite concise. Obviously, there's also some that look a bit more involved. And then there's also some outliers where you have much longer programs. Yeah. Because for some specific things, the DSL is not super adequate. Otherwise, some numbers. So as I said, there's 160 primitives, 1.5 K lines of Python code. The solution programs are about 6.5 K lines of code. So that amounts to about 10 primitive calls, like 10 lines of code for the median solution program. And the average primitive occurs like 48 times or 50 times, yeah. Just to kind of give you a feel of how this may look like. Yeah, this is one work, not by me, but people from Amsterdam that directly builds on this DSL, which was nice. There was in ICML. A little fun fact here. So here they refer to me and then write about the D and then in brackets human designer. So I may or may not be human, be aware or be warned. Yeah, and then that was all nice and good. I mean, I did some kind of prototype search over that DSL, which got me like 6%. But I felt like I didn't want to push this much further. So actually gonna get into the reasoning here, I think. Yeah, it just felt like a bit weird. Like I don't want to manually have to infuse all those priors or search heuristics or whatever other piece of knowledge you could think about that you would want a system that attempts ARC to have. But I wanted the system to figure this kind of things out by itself. Basically, I want to do machine learning. So, and obviously for that, while in the best case, you could solve ARC without ever having seen any ARC-like data, it's kind of an almost requirement, in my opinion, or at least super useful to have a lot of, or at least more ARC-like data. So that's kind of what I set out to do. The first idea was like just looking at the ARC tasks and try to tag or classify them. And one kind of schemata that neatly allows many ARC tasks is like this idea of, oh, you have some set of objects, and based on whether or not they satisfy some condition, you transform them. So I set out to write some code that basically you have a list of transformations for objects, a list of conditions for objects, and use that to procedurally generate tasks. Yeah, basically first sample condition and transformation. You create a bunch of objects and you just put that together. So this may look something like this. And yeah, like I put together 100 conditions, 100 transformations, like the cross product of those, it gives you like 10,000 tasks. And that was all nice and good. Those tasks seem to be somewhat, or all in all, valid in the sense of they look human solvable and useful. But obviously it's very narrow. Like then I was thinking about extending that, like, okay, adding more complicated conditions or transformations or multiple groups and whatnot. And by that, you could probably extend the number of producible tasks by manifold. But yeah, what about the task diversity, right? Not every task can be neatly described in this format. And what about the validity of the tasks? Like you don't want to generate something that is likely garbage. So there's some limitations here when trying to think of like classes of tasks. Obviously, the first one is you won't find like a handful or a dozen kind of classes that neatly fits all possible thinkable ARC tasks, right? And also, if you want to make one of those classes more involved, then you're gonna be struggling on the verification side. Like when you generate some task, making sure that it's also a sensible task. Yeah. So in summary, that I rated it as like a far cry from the ultimate goal, and the ultimate goal would obviously be, yeah, you have this theoretical space of all possible ARC tasks and write some piece of code that kind of manages to sample from that. Yeah.
Thanks for sharing all this so far. Quick question I have is like, humans, Petra Soler always says like, humans can do the up task rather easily. Computers struggle with it. Like, it seems that humans are inbuilt with certain priors. I'm not too sure whether these priors are naturally born with or is learned through the environment, like maybe learning physics, learning occlusion of objects, because those are used in up tasks. Like when you actually did your DSL, like how much of it, like how much effort did it take? And like how close do you think it's related to human cognition? I just want to seek your feedback on that or your views on that.
But it's a good question because in some sense, the DSL is kind of close to natural language. Like I have a primitive that's called filter or merge or like rotate. Like those are all kind of concepts we as humans also use. But if I give you kind of a random or average ARC task and the corresponding solution program in the DSL, the way you would describe it in natural language is probably still quite a bit different than what this solution implements. And I also did not try to maximize for kind of how well those primitives align with the concepts that we use when we solve ARC tasks. More like it should be allowing for short programs. But that was obviously a trade-off. But to me, it's kind of still very unclear, like if you want to do program synthesis, how much correspondence or overlap should there be? Or like how well should a single primitive map to a single concept that we as humans use, right? Because one primitive may correspond to many concepts or the other way around, right? So
yeah, it did. Actually, when I was doing the ARC challenge also, I tried to use like somewhat similar to a DSL approach. I gave a large language model some primitive functions that it can use to generate code on. And my struggle was that like I didn't know how much to give it, because the more you give it, the more specific it becomes, and then the less general it can solve. Like, if you equip someone with enough specific skills, it doesn't become a general problem solver anymore. It just specifically narrows down to that a few tasks. Like, so in a similar vein, like how do you decide which DSL functions to keep and which ones to, or which DSL functions to add in? Because you can add in very specific one, like your L shape just now. You could have added the L shape in, then it'll be 2 lines of code only to get the DSL for that program. But by adding the L shape, you don't know whether or not future programs will need to use it. So what's your criteria, or like if any,
Yeah.
to decide whether something should belong in the DSL or something shouldn't?
Yeah, I would say the first maybe 10 to 30 primitives I just came up with from scratch by not looking at individual arc tasks, but like trying to remember kind of what kinds of things occur in the corpus. But from that point onwards, it was like an iterative refinement. And whenever I found tasks where it was like either super hard or impossible even to come up with a DSL only solution program, I was like, okay, this primitive is missing, and then I added it. Not just if it was only useful for one task, but when I was like, oh, here I have those 5 tasks. If I only had this primitive, then those would be much more easily or concisely solved. That was a criteria for adding a primitive. Obviously, it did happen that I added some kind of primitive, and then another 50 or 100 tasks down the road, I realized, oh, this kind of is never really useful anywhere else. And also I can rewrite it using those other 2 primitives. And then I kind of removed it. Yeah, that was kind of guiding principles for adding or removing primitives.
Understand. So if I may summarize, you add primitives based on an initial set, and then if you realize that another primitive can be composed as 2 even smaller primitives, you delete the top one because you can already compose it as 2 smaller ones.
Yeah.
And if you go to a new task, you see that you cannot solve with any of the earlier primitives, then you add in another small primitive that can solve it.
Yeah, I don't always remove a primitive when I know that I can rewrite it using only other primitives. Actually, not at all, because at least 80% of the primitives I can rewrite using only other primitives. So I can compress the DSL down to like 28 primitives, and it still has the same expressivity. But obviously, that doesn't help me much, because then my solution programs would just explode in size. So that was the trade-off. I only really kind of removed the primitive if it was rewritable using other primitives and also rarely used. So yeah.
Understand. So can I ask like whether or not, like, because you did the DSL initially for the 400 train and the 400 test set, did you
For the training tasks.
Training and eval maybe, like, because there's a private test that's not available for us. So did you base your DSL only on the train set,
Yes,
or you use both the train and the eval set?
only on the train set.
And that same set of primitives could also work on the eval set without modification.
Correct. I mean, it resulted in slightly longer solution programs in the median, but I did manage to solve each of the eval tasks as well with the same DSL that has been like leaving it unchanged.
But is it the average length of the DSL is increased compared to the train set?
Yeah, I would say the average length of the solution or solo programs has increased a bit. Yeah.
All right. So in my understanding of the ARC challenge, it is not proportionate in terms of difficulty. The training set is easier. The eval set is like medium, and the test set is insanely difficult. At least this is what I understand of it. And given that you're a solver that could give all the DSLs for like train and eval with some lengthy DSL, but for test you got only 6%. So does it mean that maybe the DSL, okay, I mean, this is not poking at your approach, but maybe the DSL itself is not the fundamental level that humans reason at? Could this mean that? Because like, or either that or the test set is just too hard.
Yeah, I would say definitely I mean, it could be the test is too hard, we don't know, but definitely it's the case also that it's not at the same level because arguably humans have many, many more concepts of primitives. Like I have this idea of a zigzag line or an L shape or bouncing off a wall or all that stuff. All that is not in the DSL. You have to use all the primitives to construct such things. And maybe they're super involved. Yeah.
All right, thanks so much. Don't want to hold you back from the rest of the presentation, but I think that was quite insightful for myself as well.
Yeah, so let's just talking a little bit about everything else but rearc, but I think now I'm going to get to rearc. Basically, I know I was sitting in university and we were like, oh yeah, let's try to do some science or some research, but we haven't really, we couldn't really do that because there was no decent data. So one of the obvious things you could think about is, I wonder how well I could solve like those tasks if I had an unlimited number of examples for each of them, right? So maybe a step back, I would say ARC is mainly hard for machine learning approaches because there's a great diversity in tasks, right? If every kind of tasks were to follow within a very narrow kind of schema, then arguably you could do much better. And also, if you had the same diversity but you had many more examples, this would also turn ARC into an easier problem, and you could also probably do better. So it's also this few-shot nature that makes ARC hard, in my opinion. And yeah, so there was really this question, what if we had unlimited number of examples? So I started out writing some functions to generate more examples. And that just kind of escalated, and I did it for the entire training set, yeah. And this is a bit of hindsight justification, but this was indeed also something I had in mind when doing this. So it feels like a lot of people are just trying some approach on ARC, just trying to get a nice score, but few people are really doing kind of simple things, or trying to break ARC down into a simpler problem or a subproblem and trying to do actual fundamental experiments with it, yeah. So the goal with this reverse engineering effort of having more examples per task was really to enable sample efficiency research questions, and also like within task generalization capability experiments. So obviously you have this notion of generalizing across tasks. Like you have a similar task, can you also solve that one? But you also have this notion of, oh, you have seen training examples of the same task where you have seen either one or two objects or three, and now your test input has four objects. Can you still do that? For humans, it's kind of trivial, but it's kind of well known that in machine learning, you're having a hard time with that. Yeah, so I really was, or am still hoping that this data can be useful for anyone that wants to do some more fundamental experiments, yeah.
I actually like your premise a lot because, like one of the machine learning pioneers, Yan LeCun, is a big fan of this idea called self-supervised learning, where we learn from our own experiences. Maybe just, like large language models like next token prediction could be an example of that. Like you learn from the sequences in the wild, you just try to predict next token, and you can get a lot of understanding of the world. So when you say like generate more training samples to, to try to learn something, I think that's quite relevant because for ARC itself, we don't really have this like self-supervised nature to play around with. So I guess the best approach is that you give it more and more similar variations of the same theme, and hopefully the model learns something, whatever you use to solve ARC. So
yeah, I mean, I'll talk a bit more about this after showing more details about what I actually did. But yeah, I think it should be useful. At least I hope so. So yeah. Yeah, basically the outcome is like a generator function for each of the ARC training tasks. And in some sense, each generator generalizes the task, meaning maybe you have an ARC task where your grids are always 10 by 10 pixels, or the background is always black. But for the transformation to be applicable or make sense, those things need not be the case. So I try to abstract away from that and say, okay, if I generate an example that may be of any height and width and background color, and also number of objects may vary more than it varied in the original examples. Yeah. So that results in quite large sample spaces for each of the ARC tasks. You can easily generate tens of thousands, many times like millions of examples for each task. And you can also try to control the difficulty of those examples. I'll talk about that in a minute. And yeah, I also make sure that whatever I generate isn't just garbage, because maybe I've messed up something in the generator. So I provide a verifier function for each task, which I can then use to do rejection sampling. Yeah, when I say generator, this is just like a task-specific function, and it creates a new example from scratch. So I don't do kind of augmentations of original examples or anything like that. I really I sample the height and the width and the background color and whatever else you may need, and then I generate an example, and yeah. And when I say generalization, I think I mentioned this already a bit. Yeah, oftentimes in the original ARC-DSL, there's stuff that's like hard-coded or in super narrow bounds. That doesn't need to be the case. So I just loosened those constraints. I think I said all of this already. And yeah, I touched on this as well a bit. I was like, I don't just want to have those generators, and then people are like, yeah, but can I trust this, or who's to say that this is any useful? So, and obviously, like assessing all the data is infeasible because maybe I want to generate 10,000 examples for each task. So I provide this verifier function, which is just a function that takes the input, and if this input is valid example for the task, it gives you the correct output. Because the generator may at times like fail or generate an invalid example. So I can filter out those after I generate. Yeah, that was the idea. I can also, like each generator takes like a lower bound for a difficulty and an upper bound, which just controls the RNG, or like the cardinalities I sample. And the idea with that is that I can kind of try to control the difficulty of the example. So the assumption here was that if you have more elements to deal with, among other things, then your example is more difficult. So if you have more objects or bigger objects or more colors or more pixels, whatever, it tends to make things harder. And yeah, basically just takes two numbers between 0 and 1, like a low bound and an upper bound. Let's say I could generate grids with height anywhere between 1 and 30 if I provide this subinterval or those two numbers. Then each grid would be of height at most 15. Yeah. And that's kind of the explicit way to, at generation time, try to control difficulty. But there's also a more implicit way where you can just say, oh, I just use this full range of difficulties. I generate a whole bunch of data. And then after that, I order or subset this data based on some metric. And the metric I kind of suggest here is I look at the three things I think most strongly correlate with example difficulty, where obviously the difficulty is always like relative to other examples of the same task. Because it doesn't really make sense to compare this difficulty levels across tasks. And it's just like a weighted sum of how many pixels are there, how many different symbols, aka colors, and what's the kind of density of objects on the grids. And for the objectness notion here, I just went with like any set of pixels with the same color that are fully adjacent. Obviously, that's not the notion of objects that may be most appropriate for that task, but that's just what I went with here.
Could I ask a question about symbols? Because I'm not too sure what the symbols actually mean. Because like objects is a similar color, right? Then how about symbols?
Yeah, sorry for using confusing terminology here. So Francois talks about 10 distinct symbols in ARC, which he happened to encode with numbers 0 to 9, and which also happened to, if we as humans want to look at those tasks, are given a coloring. But in and of itself, those are just distinct symbols. They shouldn't bear any further meaning, as far as I'm aware. So that's why I use the term symbols here instead of colors.
Yeah, maybe a recommendation is we change this to like number of distinct colors, because
Yeah.
that's the same as symbols, right? In this in this equation.
Yes, but I think ARC itself does not say an ARC task or a grid has certain coloring. It's just the case that if we want to visualize a grid, it makes sense to use colors, right? So that's why I prefer the word symbols.
Understand? Yeah. So this PSO difficulty is like an arbitrary numbering that you just came up with, right? There's no, is there any like reason why you have decided to weigh it like that?
The weighting?
Yeah, the weighting of this.
Yeah, so like P stands for the number of pixels in input and output. And the biggest any grid could be is like 30 by 30 pixels, so that's 900 pixels. So this is just to normalize this component of my weighted sum to the range 0 and 1. So obviously for two grids at most I can have 1800 pixels.
Oh, got it. So each of the three terms can be normalized to 1, and then you divide by 3 so that the whole thing can be normalized to 1.
Yeah, exactly.
Then
And
got it.
also I can have at most, like this term would be 1 if if like each pixel has no neighboring or adjacent pixel with the same color, then I would have the same number of objects as pixels. And if the whole entire grid was just one color, then I would have one object. Sure, then this wouldn't be 0, but it would be very close to 0. But yeah, it's just really a proxy anyway. Yeah, so some small limitations. Obviously, this notion of like, oh, what's the true underlying transformation of a given task that I try to reverse engineer? That's not really well defined, probably on purpose not. So that's that, right? So I just did some interpretation of how can I understand and generalize this task. And then, yeah, kind of trying to exhaust this sample space for any given task was also quite cumbersome at times, right? Maybe if you want to have like very many objects, it becomes super hard to verify. So I just kind of made some trade-offs there as well. And yeah, the generation itself, I mean, I think it's something like 1,000 examples per second on average, but it really varies a lot. There's some outliers, so generation may be slow if the generator itself is slow, right? That's the obvious one. But it could also be that the verifier is super slow. And because I do this rejection sampling, that may make the generation process as a whole slow. And then the generator could also be sample inefficient in the sense of it generates many invalid examples, or it could also be that the sample space is small, right? If I want to sample 10,000 examples, but the generator is only capable of 20,000, then I'm gonna be waiting for a while because it's gonna be giving me duplicate examples a lot, assuming I filter out duplicate examples, yeah. Now I'm gonna show some examples of how this rearc data looks like. So this is an original ARC task, so input, output, and so on. I think it's somewhat clear what's going on here. And then if I kind of use difficulty values on the lower end of the spectrum, then I get easier examples. So those are generated examples. And you can see there's not all that many colors and there's not all that much noise and so on. And here I can obviously make things harder by involving more objects or more colors and so on. Here's another example. Again, that's the original examples. I can generate easier instances for that by having the grid smaller and the kind of lines that I need to color to be shorter and so on. And I can also make them longer, right? Yeah. And I think I have a third example here. Again, that's the original one. You just stack those together. it's easier, arguably, if objects are smaller and there's fewer of them, and so on. And it's harder if there's more pixels and colors and objects involved. Yeah, I think you get the idea. And now maybe about the interesting stuff. So what I'm hoping for, or what I was thinking is, yeah, probably we can learn a task quite well in a sample efficient manner. Probably most of those ARC tasks can be learned with some machine learning approach in like a individual manner. But that's kind of an issue, right? People always complain, oh, deep learning is like sample inefficient and so on. What about just trying to explicitly go for or optimize for using less samples, right? We can say, oh, how few samples do I need to reach a certain performance? Or what's the best performance I get from only using 1,000 or 10,000 or 100 examples, right? You could consider experiments like that. And I think that may be very nice to do, or it may give some insights. Obviously, it's not at all the same thing as solving ARC. It's like a baby or toy version of the problem, which is still related. And I think it's not super impossible that this could give us some insights, yeah. Another idea is obviously, again, a complaint or criticism of deep learning approaches like, oh, if you train of only up to grid size 10 or 20, it will fail on bigger grids. Like it can't generalize to more difficult instances. Or if your model has only ever seen up to 4 objects, it's going to fail with 5 objects. So you could also try to design experiments where you explicitly ask for the model to still perform well on out of distribution examples. Where by out of distribution, I just mean they're harder. Obviously, that needs to be kind of explicit. So pick a certain degree of freedom, like the number of pixels or symbols or objects or anything else. And yeah, see how far your approach can perform, your machine learning approach, when you go out of bounds there or exceed the threshold that your model has seen during training. Yeah. Some small side comments or outlook. Obviously, the most interesting notion of generalization is this across-task generalization, right? If I've seen a certain number of tasks and then I get presented a new but somewhat similar task, can I still do that? But that's not really addressed here. So, what I think one could think of using this data also to do some meta learning or curriculum learning experiments, but I didn't really provide any metric to make it more feasible to do that, like on a level of tasks, where you try to see how well you can generalize from one task to the other, because really rearc only provides still the same 400 tasks, so it's not really inherently suited or suitable for meta learning experiments. That's why I really try to have it focused on only those sample efficiency and within task generalization things. Yeah. Of course.
Just
Yeah.
curious for rearc, can you just give it any arbitrary DSL, like a sequence of DSLs, and it can generate syntactic examples based on that, or is it already like hand curated for each of the examples? Like, yeah, my question is, can we just give it arbitrary DSL sequences to generate?
No, it's like handwritten, like so I just like, this is referring to a specific task. I mean, it's really just this is all handwritten. Like, I just try to reverse engineer the distribution of that task by creating such a sampler. So there's nothing super fancy going on here, right? There was a whole lot of engineering effort, but there's not really any intelligence in that, right? So
Yeah, I'm just thinking whether, like based on a sequence of DSLs, whether you could just perturb the input parameters for each function, and then you can get, like, let's say, for example, I have a black square or a red square on a black background, and I shift the red square by 3 pixels to the left. All right, that's my sample task. All right, then perhaps like we don't even need to give it the test and the training set. We can just give it one sequence of DSLs, like just shift the red square to the left. And then based on some perturbation, you can perturb the go left 3 pixels, could be 2 pixels, 1 pixels, or go right 1 pixel, 2 pixel. Stuff like that. Like just taking any arbitrary DSL sequence, can we do a generator that just perturbs the input parameters?
By DSL sequence, do you mean a DSL program? Like because
Yes. Like a DSL program to like maybe solve a task.
Yeah, maybe that's feasible. Like, but the thing is, like, if you only are given a DSL or a solution program that turns like a valid input grid into your correct output grid, then that doesn't tell you how to construct sensible input grids in the first place, right? I think for most tasks, it's the case that even if you magically happen to stumble upon the solution program written in the DSL, that doesn't tell you how to come up with valid input grids, right? Because many of those tasks, maybe they assume two dots, like 2 pixels of the same color to be on the same horizontal. Because otherwise, either your program will crash or the transformation will collapse to the identity. So I just feel like maybe you could do that with a whole lot of compute, but it seems highly non-trivial to me. But obviously, that's kind of the golden goal, right? You want to procedurally generate tasks from scratch and not just procedurally generate new examples from for already given tasks. So that's really just like a starting point. Yeah. And that's also kind of how I conclude here. Yeah, I mean, it maybe to readdress your question, it's definitely something I've been thinking of a lot, but haven't really addressed all that much yet, just because I think it's really iffy and tricky to actually get it done right. Because
I understand. Yeah.
think of like a randomly sampled DSL program and then a randomly sampled input grid. Like the probability that it just produces garbage is like approximately 1. So you're gonna have to be a whole lot smarter than just randomly sampling some programs and input grids for this to kind of give you useful data. Yeah. So that was kind of it. Here's a link to code, and if you have any kind of questions that you don't want to ask now, you can also reach out on X. But yeah, I'm happy to hear any kind of questions.
Thanks, Michael, for the very insightful talk. Maybe I'll start with, I know I've been asking a lot of questions, but I just start with one question and then I'll open the floor for the rest to ask. So my question is actually related to what you said just now about the input grid and the DSL is very interlinked. So I'm just thinking about this. Can the base state be like decomposed into like maybe objects or certain shapes? And then like, you do like a game engine, right? Like Unity game engine, you can drag and drop the object onto the scene. I'm not sure if you done game programming before, like, you could just drag like avatars to the screen and so on. Maybe the baseline input could be some avatars or some objects, somewhat like the Unity game engine game objects. And then, you could say like, oh, are they exact distance? Is it near to you or further away from you? Then you can do the overlay part also. So if let's say our input is not in pixels, but in objects like a game engine, then we could arbitrarily generate the objects and we could also arbitrarily generate the DSL. I mean, granted we may not be able to solve like maze finding, those kind, because those are not objects plug and play movement kind of things. Those are like more optimization, like fitting the pieces to solve a puzzle. I don't think you can do that in like game engine state also. But at least for quite a number of puzzles involving movement or color change, I think we could generate arbitrary DSL like that, arbitrary problems like that. I mean, what do you think about it?
Yeah, let me try to share. Can you see my screen?
Yeah.
So like whether you say it's objects or not. This is like a task. You have some pattern here, and it has some periodicity along the vertical. Like no matter if you phrase it as pixels or objects or whatever, like even if you're given the transformation, like how could you possibly come up with or like arrive at the fact that you need to have a certain periodicity of greater than one for this kind of foreground object on this grid, because that's what you need to construct the output grid. So if your sampled input grid doesn't satisfy that, it's going to be either an example such that your solution program doesn't, or like an input grid such that your solution program doesn't run, hence you can't generate the output in the first place, or the output is just going to be trivial. Like you don't get to capture the kind of full spirit of the task. So I just feel like for 80, 90% of tasks, you're going to have a really hard time with like having no knowledge about what kinds of things need to hold true about the input grid other than what the transformation function is that you need to apply to the input. I hope that makes sense.
Yeah, it makes sense. It also tells me that the input grid for the test set is very, very important, because if you give the wrong input grid, you will not be able to solve the problem.
Yeah, I mean, also here, like arguably, even if you had this notion of objects, maybe if it were like a randomly shaped object, it would not at all be kind of clear how to shift it or compress it or whatever is happening here. And I think this is the case for almost any task, like especially something like this. How, yeah, kind of what are the set of constraints it needs to hold for this to be for a grid to be a valid input to that task. Even if you had the transformation function, which is already a big thing you need to overcome in the first place, right? So,
Well, I
yeah,
just thought of something. What if you
tricky.
can have a schema to generate the input grid? So basically, you define like how the input grid should be generated. Like first, you maybe do a square, then you do a line to the right, then you do a red line to the bottom. Like maybe you could have a schema that can be randomly perturbed as well. Okay, so I get your point. A lot of the other tasks, the input grid and the solution space are linked. And if you want to generate something arbitrary, it's difficult because you can't just perturb the output space. You can't perturb the process, input-output process. You also need to perturb correctly the input and make sure that it's all corresponding to each other. And stuff like objects, you cannot go out of the boundary. Also, there's a limit. There's a lot of constraints that are unseen, but they are important. If not, the task wouldn't make sense.
Yeah, maybe that's a good point. Maybe some small clarification. So people may think that the generators work such that I have a transformation function, then I sample some random input grid, but that's really not what's happening. So most of the time in the generation process, I construct the input grid and the output grid kind of in parallel to each other. Yeah.
All right, thank you so much. So now I'll open the floor to the questions, for any questions. So feel free to just either use your mic or just type in the chat whatever questions you want to ask about React.
Would it be possible to trace every input pixel to the corresponding output pixel? So there is a graph representation of how is each input pixel transformed to the output pixel. Maybe one input pixel gets transformed into 5 output pixels, different places in the output image. To modify the DSL in a way so it becomes a graph representation.
But you mean such that an output pixel could be mapped to by more than one input pixel as well?
Yeah, so it kind of generates a graph together with the images with how it how does what edges are there between input and output pixels? So the pixels that say static have a one-to-one, but those that get repeated has an implicit edge to the source object it comes from.
Yeah, I think that could be a nice thing, actually. I mean, you surely need one to many mappings, right? Because the grid size may increase, right? But you also need many to one, because let's say for this pixel, the information about the shape comes from here, but about the color comes from here. So it's kind of unclear how you would say, where does this pixel come from, right? And also here, I mean, it's a many to one mapping. But again, like, it's nice, but someone has to do this. Or you have to find already kind of an ARC complete piece of code that can do it for you, I feel. So
Right. Thanks, Simon. Anyone else would like to ask anything? I mean, it need not be about like React per se. Like if you have anything in general about ARC, I think Michael has a lot of knowledge about it. Especially if you are trying to do the ARC price, you could ask like, hey, what do you think is the distribution of the ARC data set? You know, that kind of stuff. I'm sure he knows because he has spent years looking at it. Yeah. And by years, I'm not exaggerating. It's really years. 2 years actually. Yeah.
good question. How long did the DSL take to write roughly? So it was a semester project which lasted a couple months, but was not full time. I mean, I did spend quite a while on escalating that endeavor of creating DSL to actually also writing solution programs to all the ARC training tasks. But yeah, the kind of what took up most of the time was writing the solution programs in the DSL and not writing the DSL itself, right? It's just 160 small functions, maybe an average of a handful of lines of code or less. But in order to know which kind of set of DSL functions is useful, you need to make use of the DSL. Otherwise, it's just kind of guesswork, right? So I would say maybe like 2 or 3 months, but that's including kind of my prototype program synthesis approach that builds on this DSL, which was also part of that semester project. Yeah. Oh,
Right. So maybe I read the questions in the chat, then you can answer. So it's more natural. So Anupan asks, how do you efficiently search the space of all possible programs for a particular ARC task?
you don't. Because there's not semantically, but at least like if you write it down, infinitely many programs that you can express given, let's say, my DSL. Obviously, you can say you do kind of a breadth first search. So first you try to all programs of size 1, then all programs of size 2. But very, very quickly, approximately at the level of all programs of size 2 or all programs of size 3, you're going to run into combinatorial explosion issues. So if you just do brute force search, it's absolutely a hopeless endeavor. So unless you have some really neat way of pruning that search space, you're not going to efficiently search the space of all possible programs, even up to a given size that is not too small. I mean, otherwise you kind of solve this combinatorial explosion issue that you have for any kind of naive or dumb approaches like searches. So, I mean, I was kind of trying to see for a bit whether there was like an easy way, or like, okay, can you add some heuristics such that it doesn't do certain unnecessary considerations during the search. But you're only gonna get like small improvements. That's kind of the hard problem of ARC if you try to do program synthesis in the classical, like discrete symbolic way. Yeah. Like this problem of how do you efficiently search?
Right, thank you for that. Anyone else has other questions?
So would it be possible to classify a new unseen task and identify what kind of primitives would go together with the solution for that task?
Yeah, that's a good question. So I think you're saying that because if you knew which subset of the DSL is required to solve a given task, then you would have to search less long to find a solution, right? Because you don't have to consider all the primitives. So that was the very first idea that I had. I was like, okay, what if we try to do subset prediction of the DSL? Like, just can I kind of do multi-class classification? Primitive one, what's the probability of it being useful for a program or being contained in the correct program or not? But the issue with that is kind of twofold. There's not just like one correct program. There's always like infinitely many ways you can use the DSL to write a solution program for any given task. And also, like, let's say your solution program for that task, the shortest solution program uses 10 different primitives, which is kind of average out of those 160. Like, even if you have 100% accuracy at this sub-problem of predicting the subset of correct or useful DSL primitives, you're still going to have a hard time brute force searching over that, right? You just kind of made the combinatorial explosion problem like slightly less severe, right? But let's say, yeah, it's basically the same problem. So, but yeah, it's a. I think maybe you can still make it such that it gives you slightly better performance, but unfortunately, it doesn't really solve the issue, I think. Unless maybe you had a better DSL where on average you would only use like 2, 3, 4, 5 primitives, then you can brute force, but also then you're not going to get 100% accuracy because you're probably going to have more than 160 primitives, and it becomes exponentially harder to do this subset prediction. Yeah, so the idea is nice, but the implementation is hard, and even if you nail it, it's going to not give you all that much. Yeah.
So what if it's a classifier that identifies what primitive goes before another primitive? So it does the ordering of two primitives.
Yeah, I mean, obviously, if you try to, I mean, this is, by the way, this is all contingent on having a lot of labeled data, like not just many tasks, but always like a corresponding solution program. Otherwise, you're not going to learn that, but you'd have to hard code it. So, assuming you had magically been given such a set of data, sure, you can try to do more than just predicting the relevant subset of primitives that you want to use. You could try to think of repeatedly doing that or giving feedback to the model, or I don't know, trying to, for each primitive, also predict how often it should occur or in which position of your program it should occur or any kind of thing like that. But I think it's super hard to be made to work. Yeah.
All right. So thanks for the answer. Simon, do you have anything else you want to add, or you're okay with that?
I think that was it. How has it improved on your team in the ARC AGI prize on the leaderboard, you have a quite good score. So including ReArc in the training data.
I will want to keep this focused on ReArc or also better DSL, not about my team's approach, since it's like a competition. So not to make sense.
But don't worry, Micahel Hodel is Micahel has told me that like after the competition, his team will likely be sharing it. So that one I will leave it to them to decide like whether they will share it. But definitely I hope that they will share it because everyone can learn together. So the next question we have is from Anupam. A follow-up question is that, LLMs are quite general like problem solvers. So in the ARC challenge, in what capacity do you recommend using these LLMs? Do we use them for program synthesis or program search, or you recommend not using them at all?
Actually, I don't make any recommendations. I just recommend to actually try out whatever you think may work. And then if it doesn't work, ask yourself why, and then try something else, like actually try things. That's what I would recommend, whether that be LLMs or anything else. And there's kind of two obvious ways in which you can use LLMs for ARC. You can try to directly predict the output grid, give it only the task data, or you can try to let it predict a program that you then run and see if it produces a grid, right? That's what Ryan Greenblatt did with GPT-4o, which got quite a nice performance in the public data, but also which cost quite a lot. So I like the idea of going end-to-end, so directly predicting the output grid. But the advantage with trying to use LLMs for program synthesis instead is kind of, it would be more interpretable, like, right? Not necessarily, but you have a program that you can then look at and which should explain you what the model thinks the transformation from input to output is. So maybe you can make more sense of such a thing as if you let the model directly give you the output. But there's also other ways to use an LLM you could think of. You already have a sketch of a program or a guess of a program, and you give that alongside the actual ARC data to the model, and then you ask the model to refine that program. Or you could ask the model not to give you a fully working program, but to give you a sketch of a program, and then use many kind of prompts to the model to refine that. Or like, there's really many ways I think LLMs could be used to address this. Yeah, but I'm abstraining from like making a recommendation here. So
Yeah, thanks for the answer. Actually, I have a follow-up question on that. So my question is actually, in the DSL, based on what I understand from the code, it is a list of sequential functions that are executed one after another. That's my understanding. So correct me if I'm wrong.
Wait, the IceCube DSL or my DSL?
Your DSL.
No, it's really just like a library or toolbox of functions which vary in signatures. So some function may take 1 or 2 or 3 arguments. They may take an object and a grid or a number or 2 numbers. And really they are meant to, they can construct a program graph, but it's not just a sequence of operations. It's a graph.
I understand. So the later functions can reference the earlier functions to form some form of computation graph. But the thing is, like I noticed that there's no like if-else statements inside there. It's really just the modular functions executed one after another. Have you considered like, because you have conditionals in as some of your functions, like would the DSL be much shorter if we could just use Python syntax like if-else statements, branching?
Don't get me wrong. I mean, I actually do have a primitive that's called branch, which takes 3 arguments, like first a group, and then an if value, and then an else value. So for most of the standard operations or operators in Python, I have kind of a wrapper function, which as a DSL primitive, right, adding 2 numbers, so or set operations and stuff like that. So it's in there. Yeah, it's really not it's really not just like a list of object transformation or grid transformation functions. It's like that, but a lot of helper stuff and very basic stuff as well. So,
All right. So I'm just seeking your like rationale of doing it as a sequence of functions versus a free code generation that uses some primitive functions as like helper functions or in the code itself. Like because there's two extremes, you see. Like what was your rationale settling on one, like which is the current one, versus like free form code generation with some primitive functions?
but I mean, I have some primitive functions, and it's totally left up to the user how they use that to generate code, no, or programs. I think I'm not sure I understand the question.
Oh no, because like the solutions that I saw, like of the 400 train and 400 eval, it is pretty much like a list of functions executed one after another as the solution space. So like perhaps, if you could just do like some form of extra code to wrap around the functions, like it might significantly decrease the length of the solution.
I mean, yeah, like I just wanted to have this format. Like oftentimes when I manually wrote a solution program to a given org task using the DSL, it didn't look like that where you have like just one function call per line. It's just that I thought, let's bring it into this format as kind of equivalent, and it's easier to deal with. Let's say you want to do some analysis, or you want to use it as a starting point for program synthesis or program mutation or whatever. It should be kind of more straightforward. And also it's, I mean, even something simpler, like it makes it easier to measure the size of a program. Yeah.
Actually, that makes sense. Like if you constrain the primitive functions to like a sequence, you restrict the kind of permutations also. It'll be a much more, how do I call it? It's a much more boilerplate solution than arbitrary code.
Yeah, but it's not like, I have actually code to go from one format to another. Like you can basically flatten it such that you have one primitive call per line, but I can also go from that format such that I kind of insert everything into wherever it occurs in the lines below that. And then at the end, I'm given like a very long string. And so basically a flattened program, but flattened in the other direction. But yeah, you could think of anything in between as well. It's really just like a representation.
I get it. I mean, any Python program can also be treated as a list of functions because assembly code is a list of sequence, right? I mean, you could just compress it down to that format as well. And you can also go back to code. So I get what you're doing. Cool. I mean, that's a thought, like, because I'm more of the fan of the open code approach. But I also know that if the problem with like solution spaces is that if you make it too general, it's very hard to plan and generate that space because it's too general to generate too many possibilities. So constraining the solution space is actually quite an effective way of getting more reliable output. So
yeah,
I can totally understand that.
yeah.
So
but also it was really hard. Like on the one hand, you need to have your DSL expressive enough, right? You don't want to have an ARC that you can't solve with the DSL. But on the other hand, like that kind of leads you to creating a Turing-complete language, which again, you're gonna have issues with because it can just basically do anything, right? So
yeah, the more restrictions, the less general. That's what do you call that? That's a trade-off. So
yeah.
like for app tasks, you want it to be specific, but you also don't want it to be too specific. If not, you can't solve general tasks.
Yeah.
So I think the problem of the ARC challenge is that you don't know beforehand what kind of primitive functions will be used. It's like going for an exam without the prep materials. So this is the difficulty of the ARC task. And like I think a lot of solutions right now is trying to reverse engineer what are the prep materials needed. So if this is my feedback for the ARC task, nothing to do with Michael. If we already have been given the prep material, say, hey, these are the kind of things that will be tested, I think it'll be a much more fairer test. In my opinion, yeah, basically fix the primitives and then see what combination there is.
Yeah, but like, what do you mean fix the primitives? Like, how do you define the primitives? Like, is it like any set of functions that's like expressive enough to solve any of the hidden test set puzzles? Like,
Yeah, definitely.
yeah, but if that's the case, then Francois can just give us like a simple instruction set of like 10 or 20 things your code should be able to do and say, oh, those are the primitives or concepts, right? Because everything downstream or more complex, you can just build as a composition of those. So problem solved for Francois. So, I mean, it is a hard test.
I think he gave some like guidelines, but I'm not too sure whether he gave a formal list of stuff.
Yeah, he has like those core knowledge priors where he talks about things like objectness or algebra or topology. But this is not well-defined stuff, like or like agentness. What does that mean? Like how in code, what is agentness? No idea. So
yeah. And like how do you like do stuff like navigate a maze or this very arbitrary stuff? In fact, actually ARC is trying to do what you experience over time into a single image. So it's like how the ball bounces or the light bounces over the mirrors. You know, in real life, maybe if you see the ball bounce, you could see the trajectory, but in ARC, you only see the end outcome because it's only one slice of time. And that slice of time is usually all the way at the end. Like blocks at the center and fall down by gravity, you only see what happens at the end.
yeah,
So,
I mean, sorry, will you go ahead?
yeah, no, so I wanted to ask this because I think Simon had another question, and I'm just trying to segue to that. Like, so he asked, like, would it be possible to animate like maybe the maze solver like kind of task, like so that all tasks have an animated solution?
Yeah, it's a good question. So I've actually thought of doing something like that because arguably for a non-significant or like non-negligible amount of the ARC tasks, you can indeed think of transformation from input to output as like a sequence, and input is just the first frame and the output is the last frame. It's not always like that, at least not in the 2D plane, right? If you have a rotation, you can also say it's a sequence, but how do you discretize it? And you can't do it in 2 dimensions really neatly. So, but for quite some tasks like the maze solving or drawing lines or extending lines or whatever, or moving objects, obviously that's the case, right? And indeed, I mean, I've heard more than once that maybe it's an interesting thing to think of using a video model instead that has learned those priors, like moving or whatever, from sequences of frames and not just sequences of frames of length to like AK input and output. So I think for quite some out tasks, they could be useful to do. And but I haven't really I don't plan to really do that. But I definitely think to really specifically address your questions, yes, for the maze solver, definitely you can animate that.
How big a change will it be to your DSL to add animation support?
It wouldn't be a change to the DSL because that's like the sequence of frames, like whether or not that applies to a given task or how to construct that sequence of frames, that's something depending on the task. So it would be a modification of the generators. Sometimes it would be a small change because, or it would be a modification of the verifiers, right? So it just returns a sequence and not just a single frame. But it's like task specific. It's not just, oh, I do this modification to each verifier and then it returns me a list of frames as opposed to a single output grid. Because the way in which a task is solved, it always varies, right?
It could be interesting seeing for all the examples how they were built from the ground up in an animated form together with the solution.
Yeah, I mean, I had something like that for visualizing the transformations, where basically I inspect the transformation code that I have, and at each point in time where I have a grid as a type or an object, I just add that as a frame to a list of frames, and then I can plot this list. But for the generation, I mean, it would be super tricky and like a huge manual effort. It's not just like, it's not that I can just make some changes and then for all the 400 things, it will produce me something nice, unfortunately. Yeah.
It's something I've missed a lot with the Arc Interactive, that I have it for the test pair, an animated solution, but I don't have it for all the example pairs. So it's on my wish list. Swap the examples around with the test so people can solve the examples themselves. So there's some explanation of how did the task, how was it graded some way. So it perhaps could play back the frames in reverse, so you could see.
Yeah, but like that's again the point. Like some tasks are just like non-invertible. Like if you pick the biggest object and the upgrade is the biggest object, like okay, now give me the inverse. It's like give me the input grade that corresponds to that. Doesn't work, right? Because there's infinitely many, not infinitely, but yeah, very many different inputs that it could have come from. So it's like that's the thing with art. Like each task is kind of unique and novel. You can't just like find like one neat framing or class and squeeze all those tasks into that. It's yeah.
But it could be some kind of captioning together with the animation. So you could see it's a mass of the biggest object that gets selected.
Yeah. Okay. I think this one, maybe we could continue the conversation another time, because I think this will take quite some time to say. Like, and now, but thanks for the question, Simon. Yeah, really love your work on the up and doing the input output grid sizes and so on. So now, Yassine, you wanted to ask something? You can go ahead.
Yeah, hi. So I'm just wanted to jump back into the conversation about the program synthesis thing and Micahel dataset. So to answer to you actually, John, I mean, what you see is that the dataset that Micahel has created actually is quite expressive and a pretty efficient way usually to go from the input to the output grids, often more so than, for example, using a raw Python program, which you would need to have like all the functions done from scratch and so on. So in terms of line of code, I think the average solution for the training tasks actually should be something like 20 lines of code or something like this if you use the DSL from Micahel. But the big question that I have is, if you do LLMs with program synthesis, what is the most interesting thing to use? Whether it's to use, for example, Micahel DSL or it's using Python. The reason why I'm asking the question is because if you use LLMs, especially pre-trained LLMs and so on, you most certainly will have seen more Python code than DSL code, right? So the programs are more used to actually dealing with Python. However, for specifically ARC, it actually makes more sense to use the DSL, but you will never match the amount of data with the DSL that the model has seen with Python. And this, I'd be curious to know if anyone has an opinion also in the conversation about that specific thing, because I think it's a fundamental question. What language is the most interesting to use if you want to do program synthesis with R?
Question to John or to me? Sorry.
I mean, to you, if you have an opinion, and
Yeah.
if anyone has an opinion, I think it's like, I don't think there's a clear answer to. So I mean, I'd be curious to hear anyone's opinion on this.
Yeah, I mean, obviously people can discuss here, I guess. So I don't have too much to say, but I think it's definitely a very interesting point because, as I said, Python may not be the most adequate level on which you want to do program synthesis for ARC, in theory, but also Python happens to be something that the model knows much, much better how to deal with than any random DSL it probably has never seen before, right? So I think you will probably have to, or would probably want to fine-tune a model on like annotated ARC data, like annotated with the DSL, or some form of data that conveys how the DSL works, which may be super non-trivial to come by. Yeah.
I think this is where my approach and Michael's approach differ. I believe strongly in context prompting of the LM. So I will just prompt the LM with like a one-shot example of how the primitive function works and ask it to generate some code. So I achieved some success with that, like about 45% solve rate on 111 training set questions. But I do know the validation set questions are much harder. And it may not I have this suspicion that ARC was designed not to solve with code because some questions are really hard to solve with code, like, the light bouncing and stuff, flood fill, to a human, you could just fill up an object with a certain color. But in code, you need to do like a for loop. You need to check whether the neighbors are adjacent, whether is it filled or not. Like a simple task for humans, like filling up a square with yellow color, maybe takes 5-6 lines of code.
But
Here you have to differentiate within something. So whenever you talk about solving ARC solutions, you have two different problems. You have first identifying the pattern, and the second one is building the solution itself, right? So it might not be like the same kind of problems, I think.
And they may also not be super separate, like at least when you switch. But also, like, we should probably differentiate between like how it feels to us and how it would look like if you were to try to extract all the operations that happen in the brain when solving an ARC task, which is probably arguably much more involved than any kind of solution program with a DSL. So
yeah, so actually this points to the fact that I think the ARC challenge, when it was derived, it wasn't derived with programs, it was derived with core concept priors, objectiveness, agentlessness, and so on. And actually all this are just fit in the pixels because pixels are the most universal way, according to Cholet, of representing it. So in order to solve the ARC challenge, we cannot just treat the thing as pixels. So that's why a lot of people have said, oh, we need to go object view. Right. So for me, I use both object view, pixel view, grid view, different same color view, and so on. But I found that different abstraction spaces increase the performance of the solution because you can view things differently. Because ARC cannot be viewed as pixels only. It must be viewed as like objects interacting with one another and so on. So the more kinds of understanding that you have over what this pixel actually represents, what concept it actually represents, the better chance of solving it. Because solving ARC must be done at multiple abstraction spaces. You cannot just do it on the pixel level only. The difficulty is how to get all these spaces. Yeah.
Yeah, I totally agree. I mean, I view also in terms of data generation, it's like there's this kind of holy trinity. Like you could say some of the ARC tasks are best addressed at the level of objects. Some others are best addressed at the level of pixels, and you may want to think of some kind of cellular automata or something along those lines. And then some other tasks, you can just take the entire grid and take a grid level view. But also you can say, oh, it's all kind of the same. You can just parse the grid into objects, and those objects may happen to be the entire grid or a single pixel. But yeah, you could definitely gain stuff from nailing a system that gives you an adequate representation, even the right set of objects, right? Because it's not just that there's only one way to parse a grid into objects. So I definitely think there's a lot to be done there, and also many people are trying. I mean, I think most of the program synthesis approaches, they work, they have some kind of parsing and work on the level of objects. Yeah.
Yeah. So while our discussion was about whether to use code or DSL, I think the more fundamental discussion is actually like how do you represent and the concept that you need to, what's the base unit? This is unsolved.
Yeah, that's a good point. So I kind of try to more or less do what François outlined in the paper, like construct a language or a set of primitives capable of solving ARC tasks. But that really cuts it short, because if you view building a DSL as a way to infuse those concepts or priors into a system, then it's not enough to just have this library of functions that you can use, but there's a whole lot of human knowledge about how those interact, or which primitives are useful based on or conditioned on how the input grids look like or the examples look like, which is all not part of at least my DSL. So don't think of my DSL as some way of capturing all the core concepts that François listens. It's just a set of functions that you can use to construct programs. And there's a whole lot left to be done if you want to do that efficiently. So probably, maybe there needs to be more work on a DSL level, probably, for such approaches. Yeah.
In fact, I would like to just add on that the primitive functions are actually based on how you view your input. And so just now when I was saying like, hey, you could just perturb your DSL, and then Michael said that, hey, no, we need to also take care of the input. So input space, the kind of processing space that you are doing it, will actually have different processing functions or primitive functions associated with that space that you use. Like if objects, you can shift the objects. Grid, you can rotate the grid. I mean, you also can rotate objects and so on, but the different kind of input spaces you view will necessarily have different DSL.
Exactly, yeah. This is all really not part of the DSL. I mean, there are some transformations that work with grids and some that work with objects and so on, and some that work with both, but that doesn't, like having that doesn't tell me which level of abstraction I should use, right? And also on the cellular level or pixel level view, my DSL is definitely weak. So you can construct like cellular automata using the DSL, but it's like not natively in the DSL.
Nice. Yassine, you got anything to follow up? If not, I will ask one last question.
It makes sense. It's yet again a further conversation that is pointing towards the fact that a good ARC solution will be an ensemble of different solutions, right? You first need to figure out what kind of task you're dealing with and what is the best representation. And based on this, either you do full grid prediction, which is what you were saying, John, or you do program synthesis. And then within program synthesis, sometimes it might be more interesting to do it with Python. Sometimes it might be more interesting to do it with the DSL. You have to, the winning solution for sure is going to be combining these different things, which kind of like puts the question of like, is it general purpose if you're doing this ensemble of completely different algorithms, right? But yeah, like, is it a general intelligence? I don't know. But for performance, for sure, this is what it is going to come to.
Yeah, that was a great conversation. I'll just let maybe Michael just maybe do a quick summary or wrap up of like whatever you want to say before we end the session.
Yeah, I mean, thanks everyone for joining. I hope some of you have some cool ideas on how to, yeah, how progress could be made on ARC. And hopefully someone can also find the re-ARCs data or code interesting to kind of use for some experiments. I'd love to see that. And yes, as I already said, feel free to reach out to me on X if you want to chat or have any questions or anything. I'm always open for that.
And
Yeah.
with that,
Thanks for having me, John.
Thanks so much, Michael, for presenting your work here. Very interesting work. And all of us are still trying to solve ARC. And I wish everyone all the best if you are doing ARC-Price. And I look forward to see like what this can bring and what kind of approaches we can learn from this to solve general intelligence. And with that, I'll end the session. Thanks, everyone.